because we will start to talk about solutions first, and then we continue with the next topic.
Okay, thank you so much.
So what do you have? Do you have any specific questions?
Not yet, but I would like to listen to the solutions.
To the solution, but actually I published it on the website. But if you have more, if you want to more, because I'm going to tell more when other people will start to come.
All right.
Because,
thank you so much.
But if you have any specific questions regarding your solution, and
I haven't seen my grade yet. I will check my grade. I haven't.
Yeah, but you know the official solution. You know the.
Yes.
Because okay, actually, Anar, can you please start recording?
Yes, I started.
You did? Okay, good, great. Because we are going to record this and to put it on the website. So the problem number 1, the easy problem. Do you see the screen, right? Can you see it?
Yes, can see the screen, can see the whiteboard.
Yeah, the whiteboard. So the question was, during the lecture, I initially spoke about the equilibrium between the liquid. Oh, hi. If you want to ask something, feel free to unmute yourself and speak directly. Because again, if you have some specific questions, then you are more than welcome to ask. If you just want to know more details about solution, then you just listen. So if there is a liquid, the liquid is in equilibrium with the gas. So liquid molecules evaporate, and gas molecule, vapor molecules, when they come to the surface, they stick to it. And when the vessel is closed, there is a dynamic equilibrium at some point, when the rate of evaporation and the rate of condensation become equal. However, that's the kind of global equilibrium that is formed and created when the surface of the liquid is flat. So when it is flat, then each part of the surface, each segment of the surface are equal. And the molecule on the surface, single molecule, which is going to escape, it is in a contact with the same number of neighbors. So that works for this part, this point, or this point, and so on. That means the escape rate is everywhere is identical. However, when the surface is convex, so for example, this is a droplet of a liquid sitting on some flat solid surface, or when the surface of the liquid is concave, the liquid inside a capillary, this surface is not flat. And on average, the number of neighbors for a single molecule is smaller here and bigger here. That means the escape rate here is higher than here. and the capture rate, probability of capturing vapor molecule here is smaller than here. That means the dynamic, there is no dynamic equilibrium here, because here the liquid is evaporating faster and condensing slower, and here the situation is reverse. The liquid is condensing faster and evaporating slower. So as a result, the droplet will, the area of the droplet will decrease, the size of the droplet will be decreasing, and the level of liquid here will be increasing, and that will even the process will be even self-accelerating, because the radius of curvature here is smaller than here. That means this surface is more convex, and this process will last until all the droplet, all droplet evaporate completely, and all liquid becomes here. That's what I described in the previous lecture. But what is just a moment. And what is I just need to turn my phone off. What is good about science is that some processes which are seemingly different, they actually may be described by the same math and the same approach. So let's take a look at our problem. Problem number 1. We have a saturated solution of some salt, for example, sodium chloride. And it is saturated, so there are many crystals here on the sitting on the bottom of the this glass, and there is a dynamic equilibrium. So that means some ions, sodium or chlorine ions, dissolve, some ions precipitate, and these two processes have identical rate because the equilibrium has been established. So that means, formally speaking, nothing is supposed to happen, because then this state is supposed to last forever. However, if we take a look at the crystal, what do we see? It's not just if, I mean, that would work fine if we speak about just this surface. So if there were, there was a large flat crystal on the bottom of the glass, and the sodium chloride solution on top of it. So the rate of precipitation, this is the precipitation, this is the solution, and these two processes totally compensate each other. So in that case, that's correct, nothing will happen. But here we see this is the same situation as previously. We have a planar surface of a crystal's face, and we have vertices in each crystal. But if we compare this situation, the solid on the vertex and solid on the surface of the vertex and the surface of the face, crystal's face, we see a commonality between this and that. In other words, this is the surface of the crystal. And if we again look at sodium chloride, each sodium is surrounded by actually 5 chlorine ions, 3 here and 1 forward, 1 backward. So this is how this, and due to this interaction, this sodium ion is being held by their neighbors. So, and for this configuration, the escape rate will be, I don't know, this rate is KF, the escape rate from the phase. But if we move to the, I don't know, left until we reach, right until we reach the crystal's edge, you find this. So here on the crystal's edge, so the sodium ion or chlorine ion, no matter, is surrounded by just three neighbors. You can you can just take any cube, take a look at it, and you will see there are just 3 neighbors, direct neighbors. That means the escape of this ion is much faster, and this is a KE from the escape from the edge. But what is interesting about, I mean, not interesting, what is obvious when you look at the crystal, and sodium chloride crystals are cubic, obviously. Big crystal and the small crystal, they have the same number of edges. Correct? But the area of their faces are different. So the overall rate of dissolution for any crystals can be calculated, but that's simple math. That's easy to do. So the dissolution rate, the velocity of the rate of dissolution, equals to what? To the surface of all edges times the rate of escape of, surface of each face. There are no, yeah, surface of each face. Wait, and there is one more, I forgot about that. There is one more component from that. There is an edge. So there are 3 specific types of the surface. This is a vertex. Oh, this is the vertex, sorry. I totally confused. This is a vertex. This is the edge. This line is edge. And this line is this, the face, right? So each crystal has a face, has a vertex, and has the has a face, vertex, and the edge. Correct? Understood? Great. And so if there are 6, yeah, six neighbors here, 1 here, 1 here, 1 here, 5 neighbors, and 1 below under this ion, right? And there are just 3 neighbors here. So for that of this atom, 1 is here, 1 is here, and 1 is here. Direct neighbors. And how many neighbors are here? So here there are 5 neighbors. Here there are 3 neighbors. And how many neighbors are here? Who can tell me?
4.
Yeah, exactly, 4 neighbors. So that means the fastest dissolution 3. The solution will be the fast here, kind of moderate here, and slow here.
Mhm.
And according to the rate of this solution, oh, sorry, again, this is a vortex. And this is the rate of the solution here is KF, sorry, KF. Here is KE, KV, sorry, and the KE here. KV and KE. So if the size of the crystal, yeah, by the way, if you want, you can annotate, you also can draw it, draw here. So if you have any questions, just draw some or point at some, I don't know, part of the screen where something is not clear to you. Okay, so if the size of the crystal, I mean the size of the crystal is, for example, L, the length of the edge, then the area is proportional to L square, right? This is L square. It's proportional. We don't care about coefficients, right? This is the overall rate of the solution from the face. This is the overall rate of the solution from the edge. And how many vertices each crystal has? 8.
Yes.
So 8 KE.
Okay.
So what do we see here? Big crystals. For big crystals, this is big. This is big, relatively big. And this is a 8 KE. For small crystals, this is relatively small. And this is still 8 K. So this is not it does not depend on the crystal size. Okay, what about the rate of precipitation? Precipitation, again, is proportional to L square. This proportional to L, because there is some rate of precipitation to the edge, some rate of precipitation to the face, and some rate of precipitation to the vertex. So we have the same, and it is proportional to the area, proportional to the length, and 8. So that means these two do not depend on the size. These two parts do not depend on the crystal size. And these two are the same. That means crystals on average are dissolving at the same rate independent on the size.
Mm-hmm.
But on average, that means that smaller crystals they dissolve relatively faster. Because okay, that's like I don't know, taking taxes from rich and poor people at the same level. For example, everybody has to pay, I don't know, $100 a month taxes, right? For those for millionaires, that's just a little, a tiny amount. For poor people, it's serious. The tax is serious. That means small crystals and big crystals are losing the same amount of material, but big crystal are obtaining more, relatively more.
So Mark, is there a critical size then, that L compared to the 8?
Yeah, why? There's just but what the criticality do you mean? What is the point of criticality? I mean, what happens?
At which point it becomes the big crystal versus the small crystal, right? When
No. If
when
when one crystal, if you have such a situation, some crystals are relatively bigger than others. Even if one crystal is slightly bigger than another, then the bigger crystal will get slightly more precipitation and slightly less dissolution. And finally, and as a result, it becomes bigger. So that's a kind of an unstable equilibrium. When at least one crystal becomes slightly bigger, it will start to grow, and other crystals will start to dissolve. And this will continue until the biggest crystal ate everything. And that is exactly, and the analogy, this is a phenomenon which pretty common everywhere, including, for example, a society when you have many, I don't know, small farmers. Finally, when one of them is more lucky, it's becoming more and more rich, finally buys the land of others, and now he creates a large farm where all others are working as the employees. And this is, I mean, this is a very remote analogy, but that's what really happened in life. So that's the first problem. Do you have questions with this solution? Is everything clear?
Yes.
Great. Now the second story. It's visibly seemingly different, but if you have a sodium sulfate, a piece of a sodium sulfate, calcium sulfate, gypsum. So it is in equilibrium, at equilibrium with its solution, where calcium ion and sulfate ion. This compound is low soluble. That means this reaction is slow and this reaction is fast. So precipitation dominates. So you will see I mean, you will have just a little bit of calcium sulfate in solution, and the solid is here, right? But how can you dissolve it? You can dissolve it when you remove something from the solution, either this or that. But how can you remove it from the solution? Both ions are not volatile, and the simplest way, there are organic molecules, big organic molecules that can bind and kind of wrap themselves around calcium ion to make a kind of a coat and prevent precipitation. Compounds like ADTA or something like that, but it's a pretty expensive solution. We have the same story, the same result, same outcome can be achieved if you do the following. This equilibrium is described by a parameter called the solubility product. Solubility product is a product of the equilibrium concentration of calcium ion and the sulfate ion. Oh, sorry. The product, that's a product, not a. I explained during the product. During the lecture, I explained how we obtained it, so I'm not going to repeat it. But what is important, this is a constant that describes an equilibrium. So that means the product must be constant, but if for some reason this or that goes down, the second component must go up. And what do we do in that situation? We add some other salt, ionic compound, that may form another insoluble solid with the calcium or sulfate. The calcium is preferable. The solubility product of calcium sulfate is 10 to the power of negative, I don't remember, the -4, if I'm not wrong. So the product of these two concentrations cannot be, is exactly 10 to the power of -4. What we know that another solid, calcium carbonate or limestone, is much less soluble, and its solubility product is 10 to the power of -9. So that means the product of calcium and carbonate ion concentrations cannot be bigger than this. So we add the sodium carbonate to the solution. Sodium carbonate is washing soda, and we get a lot of sodium ions and carbonate ions in the solution.
Mark, I have a question.
Sure.
What determines that solubility product? Is there some kind of a chart that we look up, or do we calculate that?
No. So solubility product determines is determined by the strength of interaction between, similar to that, how strongly this ion is being held by the neighbors, and how strongly this ion is being held by the water molecule. So the ratio between the strength of salvation. So there is some interaction energy between water and sodium, and sodium and chlorines.
And
to calculate that, you need a very sophisticated quantum mechanical procedures which are not really exact. So that means solubility product is something that you determine experimentally and put into. There is one site, we may record it if you want. It's a GOOLJLE.com. I was told everything can be found here, including this parameter.
Okay.
So yeah, that's something that you determine experimentally. It's very hard to predict, And actually, it is possible to predict using modern computational tools, but these computations are so costly, still so costly, that it's much easier to just to experimentally determine it and keep in a handbook in special tables. So there are a lot of tables which you can find on internet where these parameters are presented for each compound. Okay, so what happens here? When carbonate ion meets a calcium ion, they precipitate in the form of calcium carbonate. So this is our old calcium sulfate, gypsum, and this is a new crystal, calcium carbonate, limestone. And when it precipitates, calcium precipitates, what does it mean? This concentration goes down, right? Mm-hmm. But if this concentration goes down, that means some process is needed to maintain a solubility product at the same level. That means calcium, the rate of dissolution of calcium sulfate stays the same, but the rate of precipitation becomes slower because there are the rate of precipitation is a product of this and that, right? If calcium disappears from the solution, then this process slows down, but this process doesn't stop, it continues. So it is not correct to say that dissolution accelerates. In reality, the precipitation decelerates, and dissolution continues with the same rate. And but if more calcium is coming to the solution, then more calcium carbonate is precipitating. And this process will continue until what? Until all the all the calcium sulfate is dissolved and converted immediately into calcium carbonate. So, in other words, if you take a piece of, I don't know, piece of equipment, I don't know, teapot, covered by insoluble calcium sulfate precipitation, add the washing soda solution, and you may boil it to accelerate the process, or just guys, can you please mute yourself? Someone is I'm hearing the background noise. Thank you. Please unmute yourself if you want to ask something. Otherwise, mute yourself because. Okay, so if you put this solution on the top of calcium sulfate and leave it for some time, finally this precipitation will become, this deposit are not calcium sulfate anymore, but calcium carbonate. But what do we know about calcium carbonate? Calcium carbonate, the equilibrium between calcium carbonate and its solution is the same equilibrium as in the case of calcium sulfate. However, this ion, this carbonate ion, CO3, it produces, when in the presence of acids, it produces the carbonic acid, which is very weak and importantly, very unstable acid. So in the presence of acids, it decomposes onto water and CO2. As you all know, CO2 is a gas. That means it escapes from the solution and there will be no CO3, no carbonate ion anymore in the solution. That means we have two-step process. Actually, three-step process. First, we put calcium carbonate on top of calcium sulfate, and after some time, calcium sulfate becomes calcium carbonate. Second, we discard this solution on the top because after this, we have what do we have? Calcium, sodium carbonate becomes sodium sulfate, and calcium precipitates. So now it is sodium carbonate here. Oh, so sorry, calcium carbonate, sodium sulfate here. And the calcium carbonate on the bottom. So, okay, let me do it more clear. That's it's at the beginning. At the beginning, we have calcium carbonate in the bottom and calcium and and sodium carbonate on the top. So that's what we added initially. Initially, we have calcium carbonate and sodium carbonate in the solution and calcium sulfate on the bottom. After some time, due to the exchange, we have sodium sulfate here and calcium carbonate on the bottom, the deposit. Now we discard this solution, wash it away, and we have just a solid. And to this solid, step 3, we add some acid, and and in this reaction, this carbonate ion reacts with acid, forms sodium carbonic acid, which decomposes. That means the carbonate ion becomes removed from the solution, and the calcium cannot precipitate anymore. So the equilibrium shifts to the right side, and all calcium ion goes to the solution. For example, if you add the HCl here, hydrochloric acid, that results in calcium chloride, which is extremely soluble. But as a result, this precipitation is removed, and you have a clean teapot.
Mark, is that the same reaction as when we put, say, vinegar or some acid onto a seashell and it fizzes?
Vinegar, yes. You can use HCl is too strong as it is. Vinegar is better.
Mm-hmm.
So instead of HCl, you can use vinegar, which is more safe and less damaging to the
We did it in
teapots. Mm-hmm. What?
We did it in 2 steps. We added ammonium sulfate.
Yeah, ammonium also works fine. Sodium and ammonium are pretty same, ions that behave pretty similar. Sodium carbonates, ammonium carbonate, that's exactly, that works. That works. Any ion which produce soluble carbonate works. Okay. If you have no questions regarding the solution, then let's start with the next topic, October topic. Ready? Okay, good. So this this month, the problems are about relate to electrolytic dissociation theory, and we kind of implicitly introduced this concept previously in September, because what this concept is about. In 19th century, chemists noticed that when you take a solution of some solids, for example, I don't know, sodium chloride, table salt, or a solution of, even better, if you take a solution of sulfuric acid, dilute solution of sulfuric acid, aqueous solution, so water plus sulfuric acid, and put two wires into it and attach them to positive and negative ends of a battery. You see bubbles here. By the way, you yourself may try it at home using, I don't know, table salt, vinegar, whatever. The pure water is not good for that, but if you add something of that kind, you see that. And they easily, quickly found that the positive, the hydrogen gas, the gas that forms here is hydrogen, and the gas that forms here is oxygen. And keeping in mind that water has a formula H2O, is composed of hydrogen and oxygen, chemists concluded that the composition of water occurs by electricity. And they named this process electrolysis, which literally means electricity, and lysis in Greek means decomposition, cleavage. So decomposition by electricity. And that's what initially people believed. Similarly, when they did this with the sodium chloride, they obtained chlorine here, and actually they obtained the same hydrogen here, but in addition, the second byproduct was NaOH, sodium hydroxide. Sodium hydroxide. And the reason is that sodium is a very active metal. It immediately, when it forms on this wire, it immediately reacts with water to form hydroxide, sodium hydroxide, and hydrogen. So plus H2O, NaOH plus H2. So this hydrogen we see as bubbles, and this NaOH stays in the solution here near the wire. So, but the idea that sodium, this sodium chloride is decomposed onto chlorine and sodium is still valid. The only difference is sodium immediately reacts with water. But if we get rid of water, for example, if we melt sodium chloride, a solid sodium chloride, and that will be the industrial process of preparation of sodium and chlorine. And that is how these two materials are made in the industry in large scale. Moreover, sodium metal was prepared first by Sir Humphrey Davy, using exactly the same method, but he did the following. He took a platinum plate positively charged, attached it to a positive battery, and took sodium hydroxide, a solid sodium hydroxide, and heated it until it melted. And after that, he put the negative wire here, and he absorbed formation of droplets of sodium metal. That's how historically, that's how sodium was discovered. And obviously, in that case, there is no water here. Sodium has no water to react with, so the formation of sodium is absorbed directly. So again, the conclusion was the electrolysis is a process where some compounds are destroyed, cleaved, separated onto the parts by electricity. That's what initially people believed happens during that process. However, last time during the last lecture, I described the process of evaporation in terms of escape rate, the ratio between escape rate of molecules and the condensation rate. And I noted that when we have not a pure water, but a solution of something, the boiling point, the evaporation rate and the boiling point is decelerated. And who can remind me why? Nobody remembers?
When is it decelerate? What was the question?
When some solid is evaporated, is dissolved in water, the evaporation is slower. And that means the boiling point is higher.
That's because the ions are holding on to the
Not holding. Much simpler. Actually, it's much simpler. The evaporation rate depends on how strongly the molecules are being held and on the surface area. But if some of the volume of the solution volume is occupied by other molecules, they also are present on the surface. That means the surface area decreases proportionally to the amount of dissolved molecules. That means the increase of boiling point is proportional to the concentration of another second type molecules in mole per liter of the liquid. So that's not molarity, but molality. So normally the molar concentration is calculated how many moles per liter of the solution. That's a molar concentration. In this story, this concentration is how many moles per liter of the solvent. And that's a little bit different, but important. So molality, molality denoted by the Greek letter, as far as I remember, mu, not m, by mu, times some constant, which is called a boolioscopic constant. And this depends on the number of particles, no matter which particles they are, the number of particles. And the same, and that is why it is very convenient to determine the molecular weight. Because if you take some unknown compound, dissolve it in water, and see how much the boiling point increased. from that, you can calculate how many particles are there in 1 gram. And from that, we can calculate what is a molar mass. And surprisingly, they found that when you take, for example, 140 grams or 80 grams of sugar, table sugar, the temperature rises by K, because that's 1 mole. So K is equal to delta T when mu equals to that. Correct? Now, but if you take 23 plus 35, 57 grams of sodium chloride, which is 1 mole of sodium chloride, the temperature, the boiling point increases twofold. So it is twice as big as one can expect based on this molar mass. And similar experiments were done with osmotic pressure, with freezing, because the same approach can be applied to osmosis and to freezing and so on. And all of that demonstrated that when you take 1 mole of sodium chloride, 1 mole of, I don't know, potassium chloride, lithium iodide, the number of particles in the solutions behave like there are twice as, the number of particles is twice as big than one can. And from that, scientists concluded that decomposition onto individual parts occurs not during electrolysis, but directly during the process of dissolution. When they dissolve not like a molecule of sodium chloride, which never exists, but as a separate ions. And the sodium ions are positive because they go to the negative piece of wire. And chlorine ions are negative. Chlorine ions are negative. And these and taking into account that the negative wire is called cathode, which literally in Greek means ascent. And this word has the same root as a cathedral, because when the priest, I don't know, serves the mass, he kind of ascend to the cathedral. He go to some elevated point to serve a mass. So cathode is ascent, and anode is opposite, descent. And this is a wire to which electrons are coming, from which electrons are coming, and this wire is the wire where electrons are leaving. And accordingly, the ions which comes to a positive, negative wire were called cations, because they are coming to cathode. And the ions that move to the positive ion, the positive wire, are called anion. Anions and cations. And that means that if you take, I don't know, sodium chloride, I don't know, potassium bromide, and I don't know, calcium iodide. And put them all into one beaker and add water. What do we have here? Who can tell me? Which compound are here? Nobody can tell because what? Say it again.
Different ions, sodium ions, chlorine ions.
Yeah. And the ions, these ions immediately forget the history of their origin. So if you take, for example, I don't know, sodium iodide, potassium chloride, and calcium bromide, we may get the same composition if we calculate, if you calculate the amount correctly, if the ratio is correct. The composition of the mixture may be the same, and nobody can determine which starting materials were used. And that is what we need to know about electrolytic dissociation. And some compounds, which are called salts or ionic compounds, they do not exist in the form of molecules like sodium chloride in a solution at all. If they dissolve, when they dissolve, they already are ions. And the compounds which produce this effect, which can be, for which electrolysis is observed, are called electrolytes. Other compounds, for example, sugar, they are not electrolytes. They do not produce any effect when added to water. The water remains essentially non-conductive, or no more conductive than just pure water. So there are electrolytes and non-electrolytes.
Mark, does that have to do with the covalent versus ionic bonds of the substance?
That's a separate story, and I'm not going to talk about that specifically. But there is a group of compounds which are kind of, or maybe you're right. Maybe that's a correct question. That's directly relates to what I'm saying. What I'm going to say. If you take a compound, such a compound like, for example, sulfuric, I don't know, nitric acid, H, so its structure is like this. And when we dissolve it in water, that's a liquid, by the way. When we take this liquid and mix it with water, we do absorb hydrogen cation and nitrate anion. However, in addition to that, we still see this molecule. So this molecule is at equilibrium with the ions. So there is an equilibrium. And how can we, so that means dissociation is not complete. Sometimes this equilibrium is shifted to this side. For example, HCl is a strong acid, and we can safely assume it completely dissociates onto H plus and Cl minus. Although you can find a tiny amount of HCl molecules in the solution, but this amount is very, very small. in contrast, acetic acid, or acetic acid, which is CH, carbon, oxygen, H. It also dissociates onto H plus and acetate ion. Okay, CH3, COO. However, this dissociation is very, very unfavorable process. So what happens in reality? If you look at the solution, you find mostly this and just a little bit of that. So we have the equilibrium, but this equilibrium is not between some solid and a liquid, between some vapor or liquid, whatever, but between two liquid, each of which is dissolved and mixed with each other, water mixed with acid. Or some solid dissolved in a liquid. Yes. No? Okay. And how can we describe this equilibrium? How can we characterize it numerically? To do that, we need again take a look at the rates of two processes of dissociation and association. Equilibrium in this case is the same story. The dynamic equilibrium between two opposing processes. So, what is the process of dissociation? How does it occur? Very simple. The molecule. Okay, let me use HCl as an example. How can we describe the process of dissociation? We actually do not care about the opposite process for this story. We are interested only in that process, in the direct process. And what happens during that process? The molecule stays in the solution and for some reason it dissociates. So there is a probability of single molecule to dissociate. And for 1 mole of these molecules, the probability is, rate is K. Again, the rate constant of dissociation, small k. And so the rate is K. But this K is for 1 mole, if we have a 1 molar concentration. If the concentration is bigger, will the rate be bigger or smaller? Bigger, right? Or a single, 1 molecule dissociate with probability K. 2 molecules dissociate with probability 2Ks, right? 3 molecules with a probability 3K, and so on and so forth.
So
do you agree?
Does that means that they don't dissociate because of the water? They will dissociate.
No, they do dissociate because of the water, but each of them dissociate with the same rate. And if you have 2 of them, the probability is 2 times higher.
But eventually you will have such a huge concentration that you will have very little water.
No. I mean, I'm not talking about really huge concentrations. In really huge concentrations, there is a separate theory. We are talking about dilute concentration. But okay, if you use a modern analogy, the present situation with the coronavirus, if for one person the probability that one person gets sick is, I don't know, 0.01%. I mean, for one person. But the probability that 2 persons get sick is 2 times higher, right? The probability that 1 million person get sick is 1 million times higher. Agree? So the rate of infection by coronavirus depends on how frequently, how likely one person is may get sick, times the number of persons. Agree? The same works here. The probability that one mole is converted times the concentration of the actual concentration of HCl molecules. The square brackets, as I already explained, that's the actual concentration, not the concentration that you took when you prepare the solution, but the concentration that really exists at certain moment of time. So that's the rate of dissociation. And what about association? Association occurs like this. Two molecules meet, and with some probability, they form a single one bigger molecule. So the rate of association will be Ka times H plus, right? Because the bigger H plus, concentration of H plus, the higher probability, times Cl minus. Agree? So that's important. The rate of association depends on the product of these two concentrations. Okay, now what is important about equilibrium? At equilibrium, these two processes are, these two rates are the same, right? We have neither dissociation nor association prevail. They totally compensate each other. That means if these two parts are different, equal, that means these two are equal too. So we can draw an equation. K D times HCl equals to Ka times H plus times Cl minus. By the way, can you hear me well? Great. What is important here? This depends on just a type of molecules, a type of process. So this is not dependent on actual real solution of which particular solution did you take, on the concentration or whatever. And this, in contrast, this is just a concentration. So this may change. It's always better to move everything that is changeable to one side of the equation, and then everything which is constant to another side. So by regrouping, we get what? K.
Kd divided by Ka.
Correct. Instead of saying, you may just draw it, because this is drawing is enabled. Equals to what? Sorry.
That would be D divided by A? No.
I'm not sure.
Plus
But,
C.
who is good in math? How do we transform it? Oh, by the way, why cannot you transform it by yourself? Who wants to try?
Okay.
Because you don't need any chemistry knowledge. You need just simple algebra. Yes, absolutely correct. And since these are constants that describe a process non-related to, and they are non-related to any particular concentration. That means is the constant that describe a property of this compound. Not any specific solution, but the compound dissolved in water. And we call this dissociation constant, equilibrium constant, or more concretely in relation, if this process is described dissociation, dissociation constant. And this is a capital K. That rate are denoted by small k's, rate constant, but equilibrium constant are always capital letters, and that is standard notation. This is the equation which can be frequently found in majority of books, textbooks, school textbook, university textbook, but they rarely describe how to derive it. They just give it without explanation. But now we see how it is possible to derive, and that is important because, frankly speaking, I myself never remember all of that. And when I need something, I just derive it from scratch, and that's much easier because that gives you confidence. If you forget something, you can easily derive it, and that's useful. That's a useful skill which I believe everybody has to possess. And why all of that is important? This formula allows us to calculate equilibrium concentration of each ion if we have an equilibrium. For example, if some acid has and there is one specific case. One specific case. What is the concentration of water in water? How many moles of water solution is in the pure water?
1 mole?
No.
No.
It's easy to calculate. Molality is the number of moles per 1 liter of the solution, right? Water weighs 18. How many moles are that is in 1 liter of the solution? 1000 divided by 18. It is roughly 55.5 moles. That's a concentration of water in water. So instead of, if you want to, I don't know, kind of for Halloween or kind of that, you can take a bottle of water and put a label. Pure water, 55.5 molar solution. And water, like an acid, it has a tendency to, it is also a weak acid, and it has a tendency to dissociate onto H plus and OH minus. Oh. But this equilibrium is shifted to the left side. So dissociation is very weak. And the constant, dissociation constant is H plus times OH minus, times OH minus divided by H2O. But, H2O. This is roughly 10 to the power of negative 16. So this concentration is much bigger than this. And importantly, it is nearly constant. It's not, it's a very specific case. This is the concentration of water, and this is the concentration of a solvent too. That means it is useful to combine this and that and make a product like this, which is called KW. which is equal to H plus times OH minus. And this is equal to 10 to the power of negative 14. In connection to that, who can tell me what is the concentration of hydrogen ions in water in the absence of,
10 to the negative 7?
Yeah, because to this, if when water dissociates, what is the concentration of H and OH? At least from this equation, we can conclude concentration of H equals to the concentration of OH, right? Because one molecule of H2O during dissociation produces exactly one H plus and one OH minus. So these two concentrations must be equal. But if they are equal, then we can easily, in this equation, we can easily replace OH with H and get H squared equals to 10 to the power of negative 14. Does it make sense, guys? If you understand this, do this, please. Reaction tool. Use your reaction tool. Do you know how to use it? Hey, guys, are you here? Use this. Like this. Okay. So that means if H squared equals to 10 to the power of negative 14, then H equals to the square root of it. So H equals to 10 to the power of negative 7. And when we are dealing with such small concentrations, when we need, we are focused only on these, that's easy to just get rid of that and get rid of that. We already use, we always are dealing with small concentrations, so the exponent is always negative. So, and that becomes just 7. And this transformation is, this transform H plus in square bracket into parameter called pH.
Yes, pH.
So so when you add a kind of a small p to something, we by doing that we get rid of the base of the exponent and of the negative sign. So if some number is, for example, I don't know, k equals to 10 to the power of negative, I don't know, 18, then pk is 18. So that relates not only to pH, that's a kind of universal notation, which allows allow us to save time, space, and that's easy to manipulate with such small numbers. That's a way to represent small numbers. Okay, so pH literally means what? pH means how much H plus do we have in the solution. When the pH is, I don't know, 5, that means H plus equals to 10 to the power of negative 5. And accordingly, OH minus equals to what? 10 to the power of negative 9. because together they must be 14. Oh, sorry. They must be 14. This times that is 10 to the power of negative 14. That means pH and POH, they always add up to 14. So if pH is 5, POH is 9. Okay. Now the question is, how can we calculate pH for example, acetic acid? If you take 1 molar concentration of acetic acid, let's take a hydrofluoric acid, because acetic acid is, I don't like to draw it. HF is easier to draw. So HF, its dissociation constant. Dissociation constant is roughly 10 to the power of negative 4. Now the question is, we took 0.1 molar solution of HF. How can we calculate from this and that what the pH of this solution will be? To do that, the only way is to draw the equation. The equation is the equilibrium concentration of hydrogen times concentration of fluorine ion divided by HF equals to K. So we need to find this. But this is just the equation, right? Just a mathematical equation. But there is a problem with this equation. What is the problem? The problem is there are 3 variables in one equation. And what we know from algebra, a single equation with 3 variables cannot be solved. With one reservation, it cannot be solved when these 3 variables are independent. But are these 3 variables independent? To answer this question, we need to draw another equation, which is not mathematical, but a chemical. This equation, again, is the equation, the reaction of dissociation of HF. When HF dissociates, what happens? One dissociation event leads to appearance of this, and decreases the amount of that. That means these 2 are not independent. So if we took, if we take, okay, let me clean some space because I don't want to move to the second page, to the next page. Okay, if you take 1 molar concentration of FH and we denote this as CHF, what is the difference between CHF and this? What is the difference? This is the amount of HF that we took in the solution. We prepared it. We took, I don't know, 20 grams of HF, dissolved it in 10 liters of water. 20 grams is 1 mole. dissolve it in 10 liters of water, made a 10 liter of solution. This is a 0.0 molar HF. But the actual concentration of HF molecules here is unknown. This is, we use this to, you know, this is actual, and this is a taken amount. And this is what we know because we took it. We know we took this amount to make a solution. But part of this HF dissociated onto this and that. So the actual amount of HF is what? Is this minus this, right? Or we can use F minus here, but that doesn't matter because one H ion and one F ion form simultaneously. So this is the amount of HF. So that means instead of this, we can put that. Correct? Does everybody understand this step? Show your reaction. If you don't understand, ask for clarification. Okay. Next.
I'm sorry, I would like to clarify. Could we use the Avogadro's number somehow to calculate the...
Actually, we don't, because we already took 1 mole, or 0.1 mole of the solution. We used the Avogadro. Actually, Avogadro number is not needed for this calculation because in every equation it cancels. It is present everywhere in each part of the equation. It becomes cancelled.
So what is then the difference between the number of molecules we took of HF and the the value in the square brackets?
Okay. Imagine we have, that's a good question. Imagine we have, I don't know, 1 million of couples, men and women, or using this modern standard, person identify themselves as men and person identify themselves as women, and we disregard gender fluids. I'm joking. So there is 1 million of pairs of men and couples, men and women, and they are living in some country. We know they are here, and we know, I don't know, less than 9 months passed, so there is no new birth and no death. And let's suppose nobody dies. So we know there is 1 million of couples. But humans are humans. They may some divorces may occur and so on. So after, I don't know, 1 month, there may be some couples, some individuals living separately, right? We definitely know there is 1 million of couples, but we don't know how many couples are now. So the number of actual couples, the active couples, will be AB, a man and a woman, will be this, and number of men living individually is A, and number of women is B. And we cannot show how large these and these and these are, but we know that this minus AB equals to A or B, right? And we know that this equals to that because there is no other sources of free non-married women or men other than the couple that was split, divorced. Is it clear? That is absolutely the story with HF is absolutely the same. So no other. So can I move forward? Does anybody understand it?
Yes.
Because I don't want to leave anything behind. Good. So again, that means this can be replaced with that. And in addition, H, when HF dissociates, one H plus and one F minus is produced. So this equals to that. That means we can replace this with that. Correct? So after we do two replacements, what do we get? Can anybody do it for me? K, how does this equation transform? Can anybody please write it?
I'll
here?
do it.
Yeah, do it, please. That's okay. I understand it. Yes. And let me modify it a little bit. That's correct. That's correct. Let me modify it a little bit. I'll make one more step. H plus times H plus is H squared. And one more moment. This CHF minus H plus. If we compare this and that, what do we get? Let me redraw it here. K equals to H squared, H plus squared divided by CHF minus H squared. H plus. So if we compare this and that, which is bigger? Obviously, this is much bigger because HF is a weak acid. Only a tiny fraction of HF dissociated in solution. So this comparable to this is small, so we can write this. Actually, this is also the equation with one variable which can be solved. If you transform it, it can be transformed into a square equation, quadratic equation, which is solvable. But this simplification is pretty reasonable because all this formalism works for dilute small concentrations. And for large concentration situations, more complex, but we are not interested in it. Usually in chemistry, we work with lower concentration. And this is pretty accurate. If you want, you may try to solve this equation and to use this equation, and you will see yourself, the results will be pretty much the same. So what does it mean? So we transform it, we get K times C equals to H squared, or H plus equals to square root of this. That's a simple algebra, but what does it mean? pH of the solution equals to what? Okay, that's a logarithm, but whatever. So the constant, the dissociation constant is 10 to the power of negative 4. And concentration, okay, let's take concentration 10 to the power of negative 2. That's a molar concentration, 0.01 times 10 to the power of negative 2. The product will be 10 to the power of negative 6, and the square root will be 10 to the power of negative 3. That means H plus equals to 10 to the power of negative 3. And the pH is, who can tell me?
3.
Yeah, 3. That means, again, if we take decimolar, 0.01 molar HF, and dissolve it in water, the pH will be 3. And that is an example of how we predict, how we predicted the property of the solution of the acid using the just table data from the handbook, the equilibrium constant, which, because equilibrium constant is a parameter, which is a kind of intrinsic parameter of any acid. You can, if you, one of the major characteristic feature of any acid, just go to Wikipedia to look at any acid, and one of the most important parameter will be dissociation constant, or usually they use pKa, but we already know that pK means that the same dissociation constant, just this number in the dissociation constant without the negative sign and without 10. So if dissociation constant is 10 to the power of negative 4, pKa is 4. The same story as pH. So for any acid, pK or pKa, more specifically pK of acid, is 4, which is the same statement. And this is one of the most critical, important parameters of any acid. So from this parameter, we can calculate this, we can calculate other stuff which is not exactly, not completely relevant to this month problem of the month. And just a moment. And that is essentially all what you know, what you need to know to solve this month POM. Now, your question, please. You wanted to ask something.
Yes. I wanted to ask about when we simplified the equation for K.
The previous one.
This on this page. No,
This page, yes.
on the last page. On the last page, we said that the CHF is a lot larger than the number of ions of hydrogen, and that's because the HF is a weak acid. But for instance, for hydrochloric acid, would that work the same way, or?
Yes, for hydrochloric acid, it is not working in the same way.
Calculators and don't need.
No, this is the approximation, approximate solution. Not exact, but this is exact.
So
for simple case, you use just this. For more complicated situation, like in HF, in HCl, you use this.
Okay.
But this is okay. But let me. Frankly, I don't know the answer. Don't remember the answer. And again, this is a story when you just let's try. For HCl, you either can try to solve the equation, the quadratic equation, or use the chemical reasoning again. So this is the concentration of HCl, and this is the concentration of H plus, right? Yes. So they are pretty similar. they are pretty similar. That means this goes to nearly zero. And yes, you cannot, you need to solve the equation. But if you will solve the, when you solve the quadratic equation, you will see that some factors are becomes nearly zero. And as a result, you will get K, no, sorry. You will get, the answer will be, the answer that you can obtain mathematically after solving the equation will be this equals to that. But in simple words, that means all the HCl is, almost all the HCl molecules are dissociated. But again, this is a conclusion, that's a result that you will, this will be approximate result that you will get if you, when you solve this equation transformed in a standard form of a quadratic equation. That's a good exercise if you want to practice, but that's kind of intuitively clear because strong acids are nearly completely dissociated. So there is no almost no associated molecules. So if you have, I don't know, 0.1 molar HCl solution, that means you have 0.1 mole of H plus there, of hydrogen ions there. And the pH is 1. So that's again, that's obvious, just from common sense. And why all of that is important, in particular, partially because H plus is actually acid. The concentration of H plus, I mean, acids are acidic because of the presence of this ion in the solution. So by knowing how much H plus in the solution, you know how acidic it is, and what majority of acidic property of acids are defined by this ion, because other part of the acid is just is not participating in anything interesting. And by knowing how to calculate that, you'll know a lot about solution. And the same reasoning, the same approach can be used to calculate other equilibria, not only for acids, for bases, for salts, for enzymes, and the inhibitors. And if you calculate, if you want to calculate the property, the described property of new drugs, which are inhibitor of some enzymes, you also use the same math, the same algebra, the same approach. That is good about science. The math, the approaches this science use are applicable to many seemingly different, seemingly unrelated phenomena. You use just few approaches to solve a lot of things. You don't need to kind of develop separate approach for different things. And that's how it works. So good luck with your problem of the month solutions. Next time we will probably do the same. I will present solution of the next month, and we continue with the lecture for November.
Thank you so much.
Thank you.
Mm-hmm. If you have questions, don't feel free to.
Goodbye.
Email.
Thank you.
Bye.
Thank you.
Where can I find?
Yeah. The lecture.